Hello, I'm John Religas and I'm one of the lead developers of this project called the Claplock. So in this video, I'm going to show you the simulation process along with waveform in Model Sim since this project was implemented in VHDL. So before we start, I want to make a clarification here that this project is not based from a counter base but rather time based, wherein when we say time base, for each clock slots is represented per second, only 1 second. So in this project, we have a dynamic constraints here, which I'm going to show you later and make more details about it. Before we go the simulation, first we have to understand the nature of the programming part in VHDL. So I'm going to show you first the port mapping, generic mapping, signals in the test bench, processors, which I'm gonna make a small detail about it. Then next is the simulation process. So let's go first to our Visual Studio Code, which is my IDE, my personal preference. I don't like editing in Model Sim because it generates unusual encoding. Okay, enough with that. Let's go to the files. And if we check this part, we have two files that we usually use to compile. We use to code. So we have a CL test bench, which stands for test bench file. We have a component here as well, which stands for module file. And inside of this module file, it contains a lot of internal functions that we are about to see. So looking at this file, we on the from the top, we have a library that is called the STD Logic 1164. So natively, we're going to use the bit and the bit vector natively, but knowing that the STD logic vector and the STD logic produce a much better results, makes it better or a candidate for using this project. So when I say they provide a better input or output per se, they produce one of a few inputs other than 0 and 1. Those are low weak 0, which is low, weak 1, which is H. It also produces X stands for unknown. It produces Z for high impedance and U, which stands for uninitialized. So those outputs makes things quite better when it comes to the debugging part. Okay, so let's go to the generic part. In the generic part, this one's gonna be used by our test bench, and basically inside in the generic mapping, it actually shows you the constraints of the system. For instance, the number of claps to lock, the minimum length of password or the minimum claps that you have to produce during intervals of input mode, the max length and slots interval. This one is specifically used in the unlock to lock mode. So it has a time interval. Next is we have the clap width, which should be respected by these two variables. So let's say a generic candidate. So more on that on the test bench. Okay, next one is we have a port mapping and it includes a lot of signals. But worry not, not all of them were useful or were going to be displayed in the model sim because first of all, one of them, this part is actually driving this one. So let's say we have a status code that shows interpreted human readable language such as this one. So TLDR, this one drives this set of signals for use for displaying that hey, we are in lock mode or we are unlock mode such as this one. More on that later on the waveform part or in the simulation part. next we have Next we have a user input. If we have to listen for the inputs, there should be at least a signal, and this one is the CL mic detection, and this one is the LED LSTN mode. So basically, these two is correlated to each other. When I say correlated to each other, if the user uh, claps the value of the CL mic should be 1, and once it was 1, the LED listen mode will turn into 1 as well, indicating to the processors that hey, we are listening for a clap of the user. Okay, next we have LED segment display, or let's say LED that blinks per second display. So it was very useful for input modes, and you will see that later in waveform how useful it is. So basically, it changes its state per second. So for instance, if we shift to 1 second, the LED is on. If we shift to 2 seconds, the LED is off, and so on. Okay.
Enter your clap password. Code unlock.
Next is we have a CL to lock claps locks. So basically this one is for use for unlock to lock mode mechanism. So basically when you're about to lock your system, there is no need for us to input the password again, but clap very fast, and the system will detect it. So for instance, if we clock 2 times in an interval of 250 milliseconds, or let's say 500, such as like this, it will lock the clap lock. Okay, next is we have a password storage here, and there are two password storage. One for the runtime for the input of user, and one is for long-term usage. So basically, it is a storage. This one is storage per se. This one is a runtime. Okay, so now we're done in the now we're in the, we now we are done in the port mapping. Let's go to the architecture. So inside of the architecture of the module, we have multiple processors, and as you can see, there is a comment for each processor. And so far, we have a total of 8 processors with one exclusion. I'm gonna explain that later when I show you the summary of this processor, a set of processors. Let's say. Okay, so we're not going dig we're not going go dig deeper from these multiple processes because it takes a while for me to explain them, and there are lots of factors that contributes that maybe you should not discuss the processor more often, but rather let's discuss the processor through the documentation. So please check the documentation on the one who sends this whole submission, this file. Okay, so as we said, we have a total of 8 processors, and here is the following by order. So we have a password detection for malformed, non-malformed, and no password. So I call this processor name as vector bit detection, and it was only useful for the post state of the system. So the system checks whether your password is corrupted or not, and it when it detects that the password is malformed, it will call another processor called the password reset functionality. So basically, it resets the password back to 0, and it waits for another input to input a password, which is calls the number processor 2. Other than that, if we have no password, it also calls processor number 2, but not the processor number 7. Okay, so next is input for unlocking. So so all processors that is waiting for inputs is actually correlated or in sync with the test bench, and you will see that later in when we do a brief introduction to the test bench. Next is if we input a password for unlocking, there should be a password that verifies the password, and that is the password validation to unlock or retain state phase mechanism. So the name is basically much formal, but what it does is it validates the password and determines if we're going to unlock the clap lock or we're going to retain the state into lock mode. Okay. So next process is the input for unlocking. So this one it doesn't utilize the password, it utilizes for a pattern. So let's say as we said earlier, we have um, we have a signal called the CL to lock clap slots. So this one is being used to to this processor number 4. So it doesn't need a password, it needs an input of number of clap slots. So it has to be all one to reset back to lock state. Okay, the next processor is password resetter. So this one we excluded this part, or we excluded this processor in our code because the complexity of the system, and because the signal manipulation were all over the place. We intend to think that the system should only take the password only one time, so you cannot reset it again unless you corrupt the chip to reset the password, which is quite impossible if we are going to imagine the physical form of this clock lock. Next is we have a password setter. This one is actually used for every time we have no password in the system, or the system has a malform and it resets the password. Next is we have the password reset functionality, which actually resets the password back to 0. And as we said, it has a correlation for the processor number 1. So yeah. And last but not the least, we have a processor 8, which stands for set of process converter from status code to status display abbreviation. As we said earlier, these signals drives these signals, and the reason for that is we cannot drive. I mean, for things to be quite useful, we want to interpret the error codes into, the status codes into something that is much more readable, and it was declared in a way like this. So status codes has a particular case, and we set the display according to what we have in the comments here. So you might able to get a full intro of this in the documentation. So please check that. Okay. So we have finished the brief introduction to the component. How about in the test bench? So in this test bench, we have the same thing. Instead, we don't declare the port in generic. We instantiate those here in the test bench. So what we see here in the test bench, we have a constant, we have a signal. For equivalence, for constants, it was actually used in the generic map. Meanwhile, for the signal, we use them in the port map. So I assume that you know how generic and port map works, so there is no need for more information about that. So let's go dig deeper to the process. So far in the test bench, we only have one process. And the reason why we have one process is because we are having difficulties of driving signals from process to another process. Let's per se that we cannot do a ratio of 2 to 1, wherein two, s- two processors, or let's say two processes, drives one signal. It is not possible. So what we did here is to make a test bench that has a workflow. So it was all in one process that basically shows you the basic functionality of this system. There's no much to say about in the process because it has to be when you're looking at the code for the test bench, you have to divide your window with the component to further understand the process, because in the test bench, as we said earlier, there is a signal manipulation, and with the use of signal manipulation, we could use other processors to do other things. So for instance, we we instantiate these two signals, we drive these two signals into one signal to further run at least another signal, another processor, so it was quite complex implementation, but it can be better. So since we are done with a brief introduction to the programming part, we are now ready to go to the simulation part. And as we told earlier, that the process the is the way as how I define this list. So it's by order. Okay, so now we are done with the programming part. I want to show you the model sim part, wherein I'm going to show you the simulation and the waveform process. So in this project, the project was already preloaded because it takes a while to load. And it takes a while to load because there are lots of signals that are indicated here. And me mentioning that there are lots of signals and constants, not all of them were going to be shown in the waveform because, first of all, most of them only drives a particular status code to status display, as I have said earlier, and some of them were just the same as is, so there's nothing to do about it. So let me pick signals, then we're going to make the simulation process then explain it further. So I'm gonna pick this BTN discard current signal for interruption process, although I might not be able to simulate it any further, but they are working. Next is we're gonna pick the CL mic detector to show that the user is actually clapping. Now we pick the code part, the state codes that shows, the state displays that shows the current state of the system. Next is I'm going to pick the clap to lock, ICL to lock clap slots. It's going to be usable for unlock to lock facing. Next is I'm going to pick the LED LCDN mode and the LED blink per second display. And last but not the least, the pattern passwords. So here are the following signals that are very useful. So for further convenience, I'm going to arrange them that suits that makes them look nice. Okay, so I was able to arrange them to the right order. I mean, I put all the inputs on the top. I put in the middle the status displays. I put the storage on the last part. Okay, so what I'm going to do here is I'm going to simulate this all the way through the end of the test bench and explain to you further what what is happening in the waveform. Okay, so I was able to run the simulation with the use of test bench. So the only thing left is to explain how it all works. But first, before we before I show you or give a detailed information on what's happening to all of the signals, I wanna tell you that there are four phases that is going currently going on here. Three phases, which is no password or fill in the password before we do the operations of lock and unlock. Second is we are going to unlock the system. Three, we are going to lock the system again back in place. And four is just an iteration of unlock and lock to see that it is still working even after doing the first two steps of unlocking and lock. Okay. So in the first part where okay, so in the first part we have a signal that is in the ready state. All things are fine. Okay. But when we attempt to see at the 250 seconds, 250 milliseconds, there is a process that sets its sub to NPW. NPW states for no password, and it actually says that there are no passwords in the system because first of all, if we check the p password pattern st here, it's all 0 bits. So after that, there is one processor that waits for input for the password to fill in, and that is the one that drives this signal once we turn on our microphone and the listen mode. So once it once it detects that we clap, the first clap was not actually counted to the system in the runtime because we need to give some time to the user that hey, we detected that you clap. So we're going to give you 1 second delay before we actually start the sequence. So as you may see here at this part, this one is actually the representation of 1 second. And as we progress through, we have a few signals that is turning on, and I set them through the test bench. So keep in mind that I opened the following bits: the first bit, the third bit, the fifth bit, and the sixth bit. So by this point, why did I only turn on 4 bits? Why not 5? Why not 3? Why not 2? The reason why is because I haven't introduced you yet to the reason of why I set these following constants to a particular values. So I'm gonna explain this to you first before we go further to our simulation. Okay, so I set the following tap count to lock at 2. So when we are in the when we are in unlock state, if we wanna lock this clap lock, we have to clap 2 times in a specific time interval, and that interval is for 100 milliseconds. So we're gonna clap very fast, like just like that. Next is the reason why I set four bits turned on because of this. We have a constraints to follow, and I set the following bits only four, and we have a minimum of three, so I respected that. So let's say that I could turn only three or four, which is the only acceptable on bit in this system. Next is we have a clap width, which is a count of 7. So I don't know if I said this earlier that the clap width this two constant should respect the clap width. So the minimum should be the minimum or should be less than the maximum. The maximum should be greater than the minimum, and the max length should be respecting the clap width. So TLDR, uh, we set the system to have a minimum password of 3 on bits and 4 on bits as the maximum with respect to clock width of 7. So the system could only accept 3 bits that were turned on, 1, 2, 3, 4, or either 3 bits, which is should be this, and this one should be turned off. I hope that it was very clear to you that the system of how this constant or constraints work. Okay, so now we were able to add the password. um it if the password is true, I mean once the constraints were met and it's not disrespecting it, there is the one that is driven to LTC will be set to PWS, which stands for password stored state. And once that was set, the system will wait for a processor. I mean, there is another processor that waits for input for unlocking state. So now we're done with the filling the password state. Now we're going to unlock this clock. So it all starts here. So I gave at least 1 second to give more time or indication that hey, the password is here. you're ready to unlock the I we are ready to process your input to unlock this clap lock. Okay. So it all starts with this, and it's another signal that is set to LTC, which stands for LTC mode. And it only turns into LTC once we have the mic and the listen mode turned on. Okay. So we're at this part we are going to iterate through the user's input once again. And we know that we are going to turn on the 1, 3, 5, and 6 bit on. So we iterate per second, and we go into this last part. I'm gonna zoom. Okay. Once we finish all of this, we're going to drive this post state, which only shows unlock and lock, to unlock only if these bits were true or were the same as this. So once it turns to unlock, there's another processor. Actually, you know what? There are two processors that drives another signals. There's one that is QLC and there's another one that is PWV. PWB. So the QLC stands for quick listening mode, and since we set our lock to unlock mode, there's another processor that has to listen very quickly based on our constraints, and we set that to 400 milliseconds. So where is the container for that? So basically, I did hit this and show this one to show you that there are two claps needed to unlock this, to set this system to lock mode. And once we zoom in here, hang on, I hit this just to show you that there is another container which is useful from unlock to lock mechanism. So once we set our lock to unlock, there are two signals that is going to be driven, which is stands for QLC and the PWV. So once we validated the password, which stands here is password validation, uh, the QLC will be driven as a quick listening mode, then waits for a certain intervals based on the constraints that we have here. So it's very short time, and it doesn't actually driven the LED blink per second display because it's out of context at all. So at this point we driven the bits per 400 milliseconds, and once we done that, once it actually acknowledged that all the bits were turned on, uh except this one because we are in the zero base index, it's gonna acknowledge it at all. So once it acknowledges that all bits were on, it will set the lock back to the lock mode, and it sets for ITL. I mean QLC will set to ITL, and it says to into lock into lock mode. Okay. Once we are done, the lock listen state will set to ready, and everything is back to normal. So basically, I could iterate this further and further, and the results will all be the same. So uh, once we run the simulation again, it will iterate only from lock to unlock and unlock to lock. So it won't iterate, or it won't restart back to no password mode. So I'm going to show you that. Okay, so I'm gonna issue multiple run and show you that it still actually works. Okay, it's the same as this, and this part. So in this video, I was able to show you that the clap lock actually acknowledge lock and unlock states. It also detects for the password. It detects if it is malformed or not. It also detects that if you should input the password again. And it also shows that we have a certain states that we should consider so that everything is actually clear to the user. So I hope that this simulation makes you able to understand the whole process, and I hope that the concept that I said earlier actually clears for you. So that will be for now, and thank you for watching.